Minnesota Stormwater Seminar Series. The seminar series is sponsored by the Water Resources Center and the St. Anthony Falls Laboratory, jointly by both of them. The money came from the Stormwater Research Council through the Clean Water Fund. So we are very grateful to both of them. Our speaker today is Marcus Quigley. Marcus has worked in water resources engineering consulting for GeoSyntec, among other companies. He's on a broad range of national projects, including work for the EPA, ASCE, WRF, and he led the initial International Stormwater Best Management Practices Database Project. Did you design that term, or that's a long title? It's a long title, okay. Yeah, the title was decided by committee. Okay. Marcus established the Brookline, Massachusetts, near Boston office of GeoSyntec in 2008 and oversaw operations until 2014. It was then that he founded Opti RTC Incorporated. He led the company as its CEO and member of the board until this year as the first provider of software as a service products for intelligent real-time monitoring and control of stormwater. So Opti is the company that you've been hearing about, and they're changing the way that we handle stormwater. The approaches Marcus pioneered at Opti are revolutionizing the stormwater industry through the ability to automatically control important features of stormwater control measures, stormwater BMPs. In March 2019, Marcus founded EcoLucid, a company working at the intersection of technology and practice. I'm pleased to give you Marcus Quigley.
Great. So thank you very much for being here today. And yeah, what a pleasure to be here. As John indicated, I've done a lot of things over the last 25 years, and I'm going to take this opportunity to reflect on some of the context, particularly around innovation and technology. As giving kind of the cornerstone talk today, I've taken a little bit of latitude, and hopefully we'll have a little bit of fun as well. So I will just jump in here. And so what I've done is I've organized this talk around some themes, and hopefully these come together into a compelling story about where we are and where we're headed. So first, especially because we're here today, I really wanted to give some historical perspective. I think we think about technology as kind of a modern concept, and particularly in civil engineering, we come from a long line of innovation in particular. So giving some historical perspective, talking about what disruption and evolution looks like. I've spent the last decade trying to disrupt, and I'm here to talk today mostly about evolution of processes, so giving some perspective around that. We're in some interesting times, so I'm going to touch a little bit on achieving results now. It's particularly, I think, a challenging time from a regulatory perspective, but we also have real issues that are driving behavior and interest in what we do. And then dive into some of the depth of the technology itself, what I see as a shift from theory to empirical observation, talking about what data is for and who it's for, and then really concluding with putting all of this into context and a call to action at the end, particularly around how all this fits together. So I'll jump into each of these themes in the next half hour. So from a historical perspective, there's a lot of words here, but civil engineering has really, as part of its DNA, been about technology integration and evolution. I went back and looked at these timeframes where there were major milestones, particularly in recent years, over my lifetime in our practice. Invention of digital computers in the early 70s was fundamental. Personal computers arrived around 1979. Interestingly, I didn't know when CAD had begun, but around 1982, ESRI, what's now ESRI, actually put the first GIS system out of MIT online the year before AutoCAD came out. I think the adoption curve was a little bit more challenging on the GIS side, but obviously this has fundamentally changed things since 1981. Hard to believe, but during my career, the emergence of the internet and the smartphone, I mean, 2007 seems like yesterday, doesn't it? And before that, we were all using paper maps or printing out MapQuest to take with us in our pockets. And then we're seeing some new things emerge. Drones first came out commercially in 2010. This year, there will be 2.5 million drones in the United States. And we're really just scratching the surface in that regard. Then I'll come back to these key technologies in 2019, but I love this photograph. This is actually from an archive from Pittsburgh, and this is Rust Engineering, which is no longer in existence. But before the 1970s, this is what every engineering office looked like. White shirts, black ties, drafting tables as far as the eye can see. And they spent their time producing things like this. This is actually a hydrograph of, this is from the Corps of Engineers for the Mississippi River. And you guys remember the 70s, 80s, and 90s, right? This is what people were up to. But this is pretty interesting. We're gonna, I've spent my career looking at data and to put things in context, but there's something I've left out in talking about this. This is from 1871 through 1899. This is all the data from the lower Mississippi River. And at that time, this is what St. Anthony Falls looked like. This is closer to 1850. But you can imagine folks sitting at drafting tables, collecting paper records that who knows got back to headquarters in what manner. And then the reason I got interested in this data in particular was last week I was in Harvard Square with my 10-year-old, and we happened to pawn this book, which is the 1900 report by the War Department from the Chief of Engineers to Congress. And this chart is in here. I actually pulled it out on my dining room table. And just because I thought it was incredibly fun. And if you have time afterward to look at it, this is it. This is what they do. They draw this thing out, and it's pretty fragile. But if you want to take a look at it afterwards, just incredible. But it gives us some context around the fact that we've been collecting data, and that technology has really been inherent to who we are as civil engineers and water resources engineers for a very long time. In running Opti, when I left in February, we had around 5 billion data points. And I didn't compare kind of the relative magnitude, but this is probably what's collected in literally a couple of seconds now. So same kind of thing. We're not doing anything kind of fundamentally different, but certainly very different means and methods. So on disruption and revolution, history is important. But I wanted to put, this is one of my favorite graphs from particularly the last few months. I've been thinking a lot about how you bring about change that is meaningful and what types of timeframes does it take, particularly just coming out of a startup and having spent a lot of my career really pushing to disrupt some of the ways we do things. I took a step back and said, how long does it really take to do things, even when they're incredibly compelling? So this is the 20th century. And this is percent of households that have a particular technology over time. And so you see a lot of these kind of innovation curves where you get adoption, and there, you take the differential of these integrated curves and you see the adoption curve. Most of the things I'll be talking about today are down at the very bottom in our field of any of these adoption curves. But you look at something as compelling as radio, right? And the curve, and how long did it take for radio to actually be propagated across society? It's over there in blue. It's one of the steepest lines in the early 20th century. And yet you still look at each one of these increments, this 15 years, you still look at 15, 20-year adoption curves to get to something like half of households having a technology. And then some of these things, even color TV, computers, VCRs, these are like revolutionary technologies, and it's really about people and how changing existing systems. These are households and kind of societal level changes, but the same thing bears out with the internet, cell phones, and then a lot of the things we're looking at. And so when I talk about innovation, Internet of Things, where are we? We're at the very bottom in what's going to be an amazing journey over the next 20 to 30 years, you know, the rest of my career certainly. This period of time I think is incredibly exciting. Then I went back a little bit further as well. This is the uptake of printing of books following the invention of the Gutenberg press. So this is all the way from the early 1400s up until the 1800s, and a number of books published worldwide. And you look at even the idea, the fundamental idea of printing books, it is about human systems. It's about incorporating technologies into the things we're already doing and change. So as you can tell, I'm a fan of you know, kind of technical history, and but it allows us to get a nice platform for understanding where we are and maybe where we're headed, and maybe what our expectations should be about disruption, even around things like internet and iPhone and these kind of modern major societal changes. At a personal level, this is my story around OptRTC, and I think it's instructive in the context that I was just discussing. So before you found a startup, what I highly recommend is a long career doing the exact thing from a professional level that you're going to be getting into. And I think you know, it says to me there is this myth of genius in our society, particularly around you come up with a great idea and it will succeed on its own. It's a lot of hard work. Everything is a lot of hard work. So 12 years of professional water resources engineering experience and consulting, and then you know, really over the next almost decade, externally funded research, pilot projects, patents, and then ultimately in 2014, you know, 7 years after kind of the first deployments of these technologies, you can tell one of the things that happened. What happened in 2007? That's the year the iPhone came out, and fundamentally that kind of accelerated ubiquitous availability of cloud resources, you know, microscopic accelerators, these types of things, nano machines, cellular connectivity. So this period is all about timing, and then you know, the recent spin out and kind of the dramatic growth of using those technologies over the last 5 years. This year, Opti will prevent over 1 billion gallons of wet weather flow just from the marginal increase in integrating the technology. I don't know if you, I won't get into all the dots on this, but if you haven't looked at these Gartner hype cycles, they're very, very interesting. They basically every year map the major technologies that are emerging. And then they have this really nice concept of kind of maximum hype, the trough of disappointment, and then gradual adoption of technologies. And you can see things on here like Internet of Things platform, digital twins. I mean, these are all civil engineering type concepts. You know, smart robots, and then you get down into the really emerging technologies. You know, blockchain for data security, very early days. Smart dust, I won't even get into what that is, but it's super interesting. You know, volumetric holographic displays. I mean, these are things that are going to like increasingly be interesting. You've got augmented reality kind of down at the bottom, probably going to climb its way out and find out what it's really for in society. But it's already gone through kind of maximum hype, and now it's like trough of disappointment, and then we'll figure out what to do with it. But it's worth digging into. And then key technologies in water resources engineering. And I'm not going to talk about all these. I've pulled some of them out. But machine learning, AI, don't forget traditional statistics. There are incredible things to do with conventional methods and statistics with big data. You don't have any interest from my perspective getting into machine learning unless you understand like logistic regression end to end. I highly advise a very strong statistics background before kind of diving into these new technologies because there's still a lot to be gleaned there. Satellite platforms, I'm going to talk about that. Sensor fusion in particular, using different types of data together in unique ways. Automation, digital twins, new sensor types. Drones I already mentioned. I'm not going to touch on all of these. Business intelligence platforms instead of kind of core web development. A shift to web services over software, so microservices all being put together in creative ways. Opti falls into this automated intelligent control category. unique ways to engage with stakeholders. I think we're just beginning to scratch the surface on interacting with the public. And then, maybe the most important thing is our ability to take all of these existing technologies and apply them in new ways. I'll show some examples. Some of my favorite kind of new ideas are incredibly simple things just put together in really, really creative ways. And this is what we need people for. These are the things that will not be automated, is that level of creativity anytime soon. Revisiting new tools. And then again, I'm not going to talk about all this. I think these things will be made available online. But these technologies aren't just about the technology themselves. It's creating business models and processes within organizations to use them in new ways. And the two that I have bolded here are long-term adaptive management. Instead of building, designing, deploying, and walking away and hoping for the best, we have the ability to continuously monitor what we've done and then adapt our systems. I think that's a really kind of a mega trend. And then also the ability to audit actual performance of what we do. So those two things kind of go hand in hand, but it allows us, particularly with getting this feedback, to even engage in contracts and capital projects in very unique ways that are performance driven, which I think benefits all of us. But there's a much longer list here too that are really new ways of doing things from a business and institutional perspective. So theme 3, I wanted to touch on quickly what the world looks like from my perspective, particularly, I spent a number of years working on the National Stormwater Rule for EPA, doing all the technical analysis to say, how should we structure some national regulations around stormwater in order to get good results? That went nowhere. And I am left asking the question, what does a post-regulatory world look like? We are not in a situation where we can have kind of the new Clean Water Act drive change from above. And from my perspective, we're starting to see that a lot of the drivers are coming from the actualities in our world, which frankly is maybe a better way to get places. So I'll dive into that a little bit. Really quickly, the USDA put together since 1959, again, a nice historical perspective. Our world is changing. We are urbanizing. We've gone from 27 million acres in 1959 of urban area. We're at 70 million acres. This is the only type of land use that we can't go back on. You'll see some of these other categories, we go back and forth between forest and ag and rangeland. Urbanization is pretty permanent, and USDA even comments when they put this graph out. It's interesting to see that forest is gradually decreasing. We are seeing a conversion over to pasture and rangeland. This is just US, obviously. Oh, by the way, this big jump is creation of national parks. So the blue and yellow, in the 70s, there were some large areas that were protected as wildlands. That's what that's about. I was curious, like, why is there a bump? This is pretty interesting to me around like who is engaged with water on a daily basis. This is from the natural amenities scale at USDA, and I love this one because it pulls out Minnesota. So you look at all of the Midwest, and what this does is by county, it counts up how much water is there actually present within counties. And then I did a heat map of what that looks like, and Minnesota jumps out. Like, one of the exciting things about being here, and probably the reason I am here today, is because Minnesota is engaged in these things. You've got good funding. You have a constituency and stakeholder groups that care about these resources. But this is the reason, is that these are a part of everyday life. These are the amenities that people focus on. You can see like Salt Lake, Lake Tahoe jumps out because it's such a large percentage of the county out there, and you got Pacific Northwest. I really view this as a heat map of engagement with water resources, kind of a unique perspective on that. Boy, that's a little hard to see. These are all of the impaired water bodies in the United States on the 303D list. And the reason I brought this up is you can actually see the outlines of the states. So when we talk about things like federalism and national regulations around environmental quality, this is a national regulation that gets played out at the state level. And the differences are as stark as the lines between states about how these national regulations get implemented. And then furthermore, oh yeah, you can see this one a lot better. I only showed the nutrient impairments. So these are all the categories of nitrogen and phosphorus. We rarely look at this data at this scale, but you notice, again, you can see where the state boundaries are. You can tell where Ohio is just based on what their 303D listing looks like. And this includes the TMDLs as well. And then just some, driving down Chesapeake Bay, Florida, had to throw in Minneapolis, St. Paul. Pretty interesting, and mostly lakes, not as many streams listed, but these are nutrient impairments. And then I had to pull out Ohio because you can see it on the national map. And we all know about things like Sandusky Bay and the western basin of Lake Erie and harmful algae blooms there. But they've had a lot of Ohio EPA is very engaged around the TMDL process. But you can see how these regulations play out at a state or local level. And kind of one of my favorite sayings about all of this right now is reality has a way of catching up with you. And how are we seeing this play out? It's things like harmful algae blooms. 2019, this is from the Environmental Working Group. They actually keep track of harmful algae blooms. And this is basically the map of where we're actually seeing major problems. This is not about Clean Water Act. This is about whether or not your kids and your dog can actually recreate or you can drink the water. Salem, Oregon had to shut down their entire water supply for their city because of harmful algae blooms just last year. And I just pulled out 10,000 salmon dead in Montana. This is just this year from Austin, Texas. And these are kind of the types of HABs that have been reported from a species perspective around the country. These are new drivers for us. The entire Mississippi beach system was closed this summer because of harmful algae blooms. They literally had to close all of the beaches. So these are really driving people's engagement. And then the other thing is the risk premium around climate change. You can debate all day about what's happening with the climate. One thing we know about is global sea level rise, and you can just watch it happen. NOAA has a great viewer. One of the things that's interesting to me from a technology perspective is the work that is done in this sea level rise viewer that NOAA has put together. It was literally would have been millions and millions of dollars for each entity just a few years ago. And they've basically put a viewer online for inundation under a whole bunch of coastal scenarios available. And I just pulled out some of you're able to scroll through year, and you can look at a bunch of different probabilistic outcomes. And I just picked something intermediate and went out to what I thought was maybe like toward the end of my career, what would things look like? And in Virginia Beach, you see there will be major ecological changes to the estuarian systems in particular. These are these areas that are flooded right now they're not homes or commercial property, but they're completely different ecosystems instead of open water, which is what they'll probably be by the end of my career. And then you look out to 2080, which I probably will not be around to see, but my kids will. And we're seeing something like 5 feet of sea level rise anticipated around that time. These are like real things, and these are not really that arguable. You can argue over where you are on that scale, and NOAA lets you slide those things around. But no matter what you do or what you think, reality is catching up with us in this regard. So big picture on the technology side on my fourth theme, a shift from theory to empirical observation. And I've seen this really play out. I spent my graduate work doing modeling, and I'm spending most of my time now figuring out what to do with huge amounts of data. And so I just wanted to give from my perspective, some of the most exciting things happening about data collection. I'm a mentor to a company called GIBE, which is involved in an accelerator with TNC and Techstars. What they do is they take satellite imagery and gain water quality data, but they've done something really interesting, sensor fusion, where they put ground-based observations and use that to correct the satellite data, and they get incredibly accurate water quality representations in real time. They get the entire US covered every 5 days, and they can turn that directly into a web service as essentially virtual sensors. This is work that they did on sediment concentrations at, this is around 10-meter resolution for all of San Francisco Bay. And they did this work for me for the Charles. We have harmful algae blooms. This is actually just this last summer, but it shows you the kind of information they can get. This is the Lower Charles before one of the major blooms. And then you can see here, actually the lower basin was closed to recreational contact. That's what the orange represents during this period this summer in July. And then just to show you, they basically can get time series, a 10-meter resolution of the entire space, and then pump that out as real data to engage stakeholders as web solutions. Shift from theoretical to empirical, and what does it mean? This is the Chesapeake Bay model, phases 1 through 5, and then I'll show you phase 6. We started out with 63 model segments in phase 1 in 1982. Phase 5, 2009, was 1,000 model segments, and phase 6 is, this is hyper spectral satellite imagery used to evaluate land use at an incredibly local level. This is on the near meter accuracy. So really, we've gone from having to do things very theoretically to more and more using ground data to actually drive our decisions. But we're still from an actual data collection on the water quality side at a very rudimentary stage. We spent tens of millions of dollars on these models. These are the calibration points. And you can imagine with where we are with IoT, and over the next 20 to 30 years, this will go from sub 100 calibration points to probably tens of thousands as we evolve things like nitrate sensors. We have real-time nitrate sensors that are robust in the environment. They're very expensive now, but these things are changing very, very rapidly. And you got to ask yourself, what is the role of those models, which are hugely over-parameterized right now with little data? What are the roles of those models and processing of data in context when we have hundreds of thousands or millions of measurements in real time about what's really happening with nutrient cycling? Theme 5, the data is mostly for the machines. So when you see a commercial about Internet of Things or I think kind of modern business intelligence, it invariably is a bunch of people standing around a monitor or looking at a report or a dashboard of some sort, and they've got some revelation about what all the data means. I don't think the world looks like that long term. I think largely people are going to be unable to actually process the information in order to make the decisions. And this is one of the things we focused on at Opti. But the satellite side, it's true of as well. The incredible amount of information. Right now, Planet, this is from Planet Labs, they can collect an image. This has only been available in the last couple of years of every point on Earth once a day. And in civil engineering, water resources, we haven't even begun to figure out what that means. This isn't just about doing the old things kind of in new ways. It's really asking questions about, can we do completely different things with these types of data? And then just to give you an idea, there are about 2,000 satellites in orbit right now, which sounds like a low number, right? I mean, we've been putting satellites up since Sputnik in the 1950s. We're only at like 2,000, and it's in the, it's around 300-400 that are Earth observing satellites. Over the next few years, we will be deploying over 1,000 a year. And from a privacy perspective, I think we all have real questions about what that means. What does it mean? There's one company right now that is saying the next 5 years, they'll be taking not one picture a day, but 70 a day of every point on Earth, including live video of what's going on. And this is really quite, let's say, evolutionary. It's going to take a while to integrate all of it, but also really gives us an entirely new set of tools. This is Oroville Dam. Pictures they took literally during construction. You can watch exactly what's happening. You look at these quickly again, it's hard for us to interpret all of this, but we're going to rely on the machines to figure out what it all means, tell us what to pay attention to, and make decisions on our behalf. And then we saw this at Opti too. When you start putting sensors out in very complex systems, and you realize in order to make really good decisions about things that are over fairly short time frames, Like, you cannot have people in the loop to make these decisions. This is a series of observations of water level in a single facility and the decisions that were made and what's happening in the watershed by OPTI over this period when there were some major floods in 2018. But you don't have to interpret what all this means. The key thing is the machines are going to have to figure out what to do with all this information and tell us about it later. And we'll be lucky to figure out what it means ourselves. But the key is to focus on achieving great outcomes for people. So all of the opportunity around technology is primarily, and I think this is good for engineers and water resources engineers in particular, is taking that technology and putting it into specific context. So it is no longer the case that things like IoT are daunting, but we're figuring out what are they for. So I really wanted to talk about that a little bit more in detail. And I'll just give one example. I know in the panel discussion, Forrest is going to talk a little bit more about more specific OPTI projects, which I'm looking forward to. But I was going to mention one project in Ormond Beach, Florida, using real-time information in context to make decisions that have a dramatic impact on people. In this case, controlling a set of pumps for a series of lakes that are basically the flood control structures for a neighborhood that flooded in 2009 to dramatically reduce flooding impacts. So thinking on its own, this is during Hurricane Irma. The system was able to, well in advance of the storm, drain down the storage and create flood storage where there was none, basically by building information in context and without humans in the loop as well. Just one other project because it's such a beautiful picture, but this is a system in Beckley, West Virginia. And this pond thinks on its own. You can see it kind of in its two states, but it decides when and how to release water based on the forecast. So as I said kind of early on about OPTI, there are 130 systems in 21 states, and it'll prevent over 1 billion gallons this year of being discharged during wet weather just from making careful timing decisions. But we're just at the very beginning of those adoption curves of these kinds of technologies. Over the next 25 years, these types of things have the potential to really change the way we design and use our existing resources in new ways. So well before OPTI ever came along, this is one of the things that really inspired me around taking simple data and applying it in context. It was a study out in Washington State on salt marsh restoration, and they did something incredibly simple. I love this. They took these little tiny water temperature data loggers, which are incredibly inexpensive. They run off batteries for 2 years. Temperature is really easy to sense, very inexpensive. And they did something really clever with them. They took a salt marsh system and they surveyed in the exact elevation that they put these temperature sensors out across the whole salt marsh, large numbers of them. And then they looked at literally just the temperature differential between sediment, water, and air, and could get incredibly detailed inundation maps in a way that would be almost intractable and certainly from cost prohibitive to do with kind of conventional sensors. And it's all about not kind of very sophisticated hardware and software solutions. It's about using data in context, really simple temperature information, but figuring out exactly how the salt marsh is getting inundated and how water flows, just incredibly compelling. So low cost, high volume data in context is I think an important theme. And around products, I came up with this comparison because of my frustration with kind of general purpose, high-end scientific instrumentation, not in context. So if you're a equipment manufacturer of sensors for turbidity, you don't know what they're for. I'll tell you what, Whirlpool knows what their turbidity sensor is for in a dishwasher, and it costs 20 bucks. This is a $6,000 device. That's a $20 device. I pulled that off of Amazon. You can order 100 of them if you want on Prime. They'll deliver them for free. But the point is, this is a device that, I mean, how many of you replaced the turbidity sensor on your dishwasher? Nobody. The thing runs for 20 years with no service, and it costs $20. And the key is, it's a very specific context. It's been controlled. They've optimized it, obviously, from a commercial perspective. But these are the types of opportunities there are in our industry to really dig in on context and use information and develop solutions that are applicable to the types of problems. And they're not always expensive or complicated. In many cases, they're incredibly simple, but they're about good engineering design, creativity, and in this case, capitalism working at its best. So just one more, I look back at the history of LEDs. In 1960s, a simple red LED, they're only available commercially in the 1960s, $200. By the 70s, they were down to 5 cents. Now, I mean, you probably have to pay, like, get them in hundreds for 5 cents. But this new technology, even in the last couple of years, we're using something really simple, an IR LED with a sensor that literally just looks at the refractive index of a piece of glass with the IR going through that glass and see how much bounces back. Incredibly simple. It's a completely solid state water level sensor. It has no moving parts. It's used in industrial processes. These aren't even a couple of years old. And this is a $25 device. You can get higher end ones. This one's plastic. Spend a little more and get glass if you've got, you know, acids or oils or other things. But they're incredibly robust and low cost. Same thing, they're using the same technology for rain sensors, optical rain gauges. I don't necessarily recommend these yet unless you want to know if it's raining or not. It's the same technology they use on your windshield on your car to keep the wipers synced up. You always kind of wondered how that happens. They send a little LED IR through the windshield. If there are raindrops, it changes the index of refraction of the interface between the glass and the air to have little droplets, and some of the IR bounces back. It's the exact same technology. But we see this play out in context. These aren't probably the end state for these types of technologies, but it's incredibly exciting to be around in a time when we're starting to see very low cost, high volume data become available to us around these important water resources issues. So I'm going to wrap up just saying you probably can sense my excitement about where we are and where we're heading. But I think it's really a rare opportunity, and I think it's a good time for us to step back and think about what it all means. One thing as engineers that we're inclined to do is focus on the technology, but we really should remember this is all about people and communities. It's not just about data. And so I really want to wrap up on that, saying technology is an enabling condition, not the goal. It's an opportunity. Technology is not just for technology's sake. It's to achieve important things in context. In Minneapolis, it's probably about things like localized flooding. You know, it's about, it's true across the country. But how can we use technology to actually solve those problems for people and what matters for them day to day? In the last couple of years, literally, particularly around things like low Earth orbit satellites and Internet of Things, we can do some things we could not do a few years ago. Incredibly interesting things. And we are left now figuring out what the heck to do with all of it. You know, we're going to be spending, you look back at the printing press, we still haven't written all the great books. You know, this is the 21st century. Since the 1400s, we've been writing all manner of books. We're not done. We're figuring out what to do. We're going to have a similar trajectory. What are we going to do with all this data? How do we use it in context? And that's a fundamentally human endeavor. We can think about some of our problems in fundamentally unique ways. I would encourage you to step back from just thinking about efficiency and thinking about solving things differently. That's what it really means to be an engineer. It's not just about sharpening our pencils and reducing cost. It's about making kind of fundamental change. And then, why are those adoption curves so difficult? It's not that we couldn't have produced a radio for every household in America the first year radios were available. We could have. But it takes us 20 years to get the human systems and particularly bureaucracies on the public side to integrate some of these new technologies. And I think it's our challenge to think about how to do that really well. And lastly, I think it's really important to engage at a global scale with these issues. And I'm trying to talk about the UN Sustainable Development Goals as much as possible in presentations. It's an incredible roadmap for our world about where we should head and what, how to balance development and growth effectively with dignity for all people. And water is a big part of this. When you pull out the Sustainable Development Goals and you look at all the details, water touches on so many elements, and I've probably pulled out the main ones here. But you know, health and well-being, clean water and sanitation is obvious. Industry, innovation and infrastructure, sustainable cities, climate action, you know, actually keeping the things alive that are in the water because they're important to humans, and keeping life on land as well. I know these are big concepts. If you drill down into the SDGs, they're also very detailed, specific action items. And certainly as a practice and as an industry, I think it's a good, you know, absolute relative, absolute baseline for us to target. So I appreciate all the time and the opportunity to speak with you today. Thank you.
So what questions do you have for Marcus?
They can be small questions too. I know I had a lot of big concepts, but yes.
So where do you think we are on policy? Local consulting firm that works for private industrial clients. You know, they're looking at stormwater as doesn't have any benefit to them. It's mostly just cost. They're doing stuff just to meet the regulation, you know. So how do you see those changes coming, and when do you see those changes coming?
Yeah. Yeah, I think it's a question for private industry. It's also a question for municipalities or other regulated entities as well. You know, my thought, particularly around where technology comes in, is that if your strategy around the environment is one where not having data is fundamental to your assessment of your risk, you should probably reevaluate your strategy. So if you, and the reason I say that is we're living in a very short period where transparency around environmental impact is not ubiquitous. And if you're an industrial discharger and the only reason you don't care about stormwater is because nobody's noticing, that strategy is limited. So I think it's really important thinking forward, just to tie it back about what we're doing today, to think about where will observation of what I'm doing be in 10, 15, 20 years, and am I thinking about that? Like, I would not rule out by any stretch that any citizen 20 years from now will know exactly what you're doing. And that transparency should motivate your behavior, and you're at least start thinking about addressing risk. So, you know, in a post-regulatory world, are we going to have the federal government coming in and saying, here's some very heavy-handed regulations? I don't think that's where change is going to come from. I think it's going to come from transparency. You know, if you've got 70 images of every point on Earth, by the way, at 25-centimeter resolution, you available to anyone as a web service. This is not 20 years. This is like 5 years from now, right? At an industrial facility, not only are you able to observe water quality issues, I can tell exactly what you're doing on your property. I can tell where every truck is. I can tell where your people are. I can tell when you discharge. I mean, this is a strategy that I think is very short-sighted from an industrial perspective if you're not thinking about that world. And maybe that's a scary place for all of us to be. It's also not something that is just specific to US context. So one of the things, some of the data that I pulled out around the growth of satellites came out of last month's MIT Tech Review. And I recommend their article on kind of satellites. And a lot of it's about privacy. The government right now restricts the resolution of satellites to 25 centimeters from a national security perspective, but this is a global marketplace. There is no way that those artificial constraints will hold. So you can think, in my lifetime, in my career, we will be down to not only observing the people, we can tell which people they are. We can tell which car it is. And maybe our regulations will change around that in a local context. I doubt it will be possible to put a lid on that. And that mostly comes from the fact that you've got European satellites, you've got Chinese satellites, you've got, it's very accessible. You've got commercial satellite providers. As we've seen with the internet, the same thing is going to happen with ubiquitous sensing. So I would say those companies, cities should be thinking about strategies that live in that world and start preparing for it. Yeah, it's an interesting way to think about things. So, other questions? That was a long answer, I know.
So it seems in a post-regulatory world, one of the things we're going to need to be better at is getting market signals correct. And, we kind of think about that most often in things like carbon taxes and carbon credit trading schemes. I know that there is, for example, a stormwater credit trading program that's operating now in parts of that Chesapeake Bay region. So my question is really, how will data and technology perhaps inform how we shape those and send those market signals? Can we get beyond a fairly crude measure of, just saying X amount per ton of carbon to something a little more sophisticated with some of the technology?
Yeah, and I'll bring it back to stormwater. So I've spent an immense amount of time on this on markets. I mean, from a business perspective, looking at, how do we motivate change? Because there's a commercial outcome on the other side of that as well. So there are some functioning markets, but technology has a fundamental role to play in markets in general. The economics of functioning markets have to do with kind of the understanding of risk and kind of pricing of the benefits and costs well. And in things like stormwater markets, we have this huge disparity between our understanding of the outcomes and the benefit and what the costs are. And there's a lot of commercial opportunity in understanding the risks and the benefits in more detail. So that will drive taking a closer look at that, because kind of, any commercial opportunity, particularly in markets, is around a disparity of the understanding of risk, and you're willing to accept that. There's huge commercial drivers for understanding those things, and as technology allows us to do that, it changes the way you can price projects and capital efforts based on what the actual outcomes are. The other part of it is it's not all upside. There's a lot of things that are happening that are very inefficient, and you saw this play out. The best example is the early markets around solar. The early compensation strategies around installation of solar were not based on performance of those systems. They were based on deployments. Like, so how many panels did you put in? How many square feet? And now we're at the point where it's all around kilowatt hours actually generated, and having those markets function very efficiently. The way we're running stormwater credit markets right now is we pay for outcomes that we're completely uncertain of, which means they have to be much more expensive. So for example, most of the credit systems compensate on volume, not on the actual outcome from like a nutrient perspective, because it's been inefficient to monitor those outcomes, and that's changing very quickly. So when you can begin to monitor exactly what's happening with nitrogen or phosphorus discharges, you can create much more efficient markets. So, if the analogy with a solar panel was like, I'll pay you per square foot, but I don't care if they're facing north or south or how many kilowatt hours. Like, this is what we're doing with stormwater right now. We'll pay you for a square foot of bioretention. I don't even monitor whether the water ever gets in there, which you hope it does if it's got a good design, but those markets are incredibly inefficient. Technology in particular allows us, as I said, to audit performance and establish contracts and markets around actual performance and outcomes. And I think that's a big change that's coming and should motivate those markets to exist in many cases. Other questions? Yes.
You've already given a lot of answers to the question that intrigues me. You have described a very rapidly changing world in terms of availability of sensors and quantity of data. We have the same in the regulatory world, where things may change from one day just to the next nowadays, and other reasons for very rapid change. How can you build that into whatever solutions you propose in your work?
Yeah, I think,
if you're dealing
right.
with very ill-defined boundary conditions.
Yeah, what I've come around to is, and I think when you look at these adoption curves where this has happened in other cases, I think it's very instructive, and we have a hard task ahead of us, which is how do you do this gracefully? You know, I don't think we're going to fundamentally disrupt cities, except in some very rare cases where there are, you know, kind of specific experiments going on to do that, and vast quantities of money going into those experiments. But I think we've got to think about our existing systems. I mean, the lab gives us a good context for like how you bring about change over very long periods of time. You know, you have to work at these things in a gradual way and figure out where you're at and how to take the best of what's available and evolve it slowly. So what I'm focused on is how do you take those human systems, bring the right set of technologies and tools to those human systems that allow them to progress. But I think disruption is a little bit off the table. You know, like from the fundamental way we think about consumer product disruption, like this is not something you can easily achieve in things as complex as cities. So we've got to look for the opportunities to get the highest return on our investment that fit into the existing human systems we have, and work very hard to do that in a graceful way, particularly with the people, because the people are the hardest part to change. And so, you know, I would say I call it meeting people where they're at in bureaucracies and systems and corporations, and figuring out, you know, how do you get at evolving what they do in ways that are very positive. And so I know that's a little bit maybe a fluffy answer, but I think it's right. I think it's thinking about meeting people where they're at and then helping them to head in a new direction.
Regardless of how sophisticated our predictive models become, they still rely on a stream of data that assumes a high level of accuracy and precision. As a new generation of environmental sensors are emerging that allow us to collect a lot of data in many locations at low cost, their accuracy may be questionable. So between accuracy, reliability, and cost, which do you see as the most limiting to acceptance of these new technologies?
Yeah, so I will say cost is not. You know, a lot of the cost, as we saw with kind of a lot of new technologies, I think are ultimately being driven down. So long term, I don't think that that's the limiting factor. One of the really interesting areas of research, I think, is what the question is ultimately about, which is when you've got low cost, less precise. So when you go back to the turbidimeters, right? You've got Whirlpool, horrible scientific instrument, perfect for process control, or you've got a general purpose scientific instrument with some accuracy and precision that may far exceed what you need for a particular context. Like the answer is somewhere in the middle. These shades of gray, like there are enormous benefits to having volume of data, and that can offset the issues that arise from accuracy and precision. And it's this really interesting three-dimensional space that in context, you need to explore. So I think this could be the subject of a large number of PhD dissertations, but it's probably one of the most interesting questions of our time, which is what should we build and how do we use it in context in the most efficient way on that kind of three-dimensional space to get to results that are meaningful. The thing that we potentially give up is using data for unintended uses. So with kind of like optimization around solving a problem in a most efficient way, we do give up some opportunity to solve an unknown problem we don't know we have yet. So like when you use a less precise or accurate instrument, but it's well designed for a purpose, you also may not be able to use it in the future for something else that's maybe more interesting. And that problem is maybe more difficult to get at. But I would really, I mean, a lot of this is just basic statistics, and it's spatial statistics, temporal statistics, and looking at what that space looks like and picking the optimization point.
Let's thank him for a very interesting talk.
Thank you.
Very good. Welcome back. We are going to move into our panel discussion section of the Minnesota Stormwater Seminar Series. My name is Andy Erickson. I will be the moderator for this panel discussion. What I'm going to do is introduce our panelists, give them a minute to describe their relation to this topic. Then we'll open up to questions. So please keep the questions coming. Our first panelist on the far right side there is Forrest Kelley. He is the Regulatory Division Manager for Capital Region Watershed District. Forrest, what's your relation to this topic?
I have the privilege of working for an organization that is governed by a board of managers that really value technology, innovation, and leadership. So I have been involved in implementing some of the great ideas that Marcus has come up with and products that he's brought to market in terms of our capital improvement projects. And I'll talk a little bit more about that later.
Very good. Thank you, Forrest. Our next panelist is Stephanie Johnson. She has just recently moved into the position of the Director of Surface Waters and Sewers at the City of Minneapolis. Stephanie, what's your relation to this topic?
My relationship to this topic really extends over about 20 years of my career in doing a variety of different things, including the development and use of technology tools. So being stormwater models, large watershed scale models, and then internet tools for communications and to support decision making. And I've done that work in multiple different roles and contexts, both academic and then in the consulting world, and then most recently in the public sector. So providing me an opportunity to see this topic through lots of different lenses, I would say.
That's great. Thank you, Stephanie. Our next panelist is Steve Riedel. He is I'm going to read his title because his title is a bit lengthy. But Steve is the Regional Trade Manager for Environmental and Energy Industries and Western Europe at the Minnesota Trade Office and at the Minnesota Department of Employment and Economic Development. So Steve, what's your relation to this topic of technology and water resources?
Thank you, Andy. Thanks for the invitation again. My focus is really on the Minnesota business side. So I'm not an expert myself. My job one for me at the Minnesota Trade Office, which is an export promotion agency, is to look for opportunities for our businesses that are solving these problems. Because wherever we've defined a problem, it's also a business opportunity for a Minnesota company. So in my case, it's largely international. I'm helping them take some of these local technologies overseas, but it's also my job to help them be competitive, period. So insofar as they are on the leading edge in many cases of solving some of these problems, my job is to help promote them and promote the state as a whole.
That's great. Thanks, Steve. And we just heard from Marcus, which I think was a great background and context for this discussion. What I'd like to do now is start to take questions. I will ask a general question to get us started, but I do encourage audience questions, both from people in the room as well as online. So please have your questions ready. My first question, I'm going to start with kind of a general question here. Given what we've heard from Marcus, right, and what you each know about using technology and water resources, how do you see technology being the most beneficial in maybe some of the different areas that we encounter in water resources? Things like communications, outreach, decision-making, planning, and operations. How do we use that best? And anyone can start.
Well, obviously, communications have evolved a great deal with Marx's timeline of when we all got iPhones and cell phones. We're expected to be available all the time, and we can take that out to the field now. So just from perspective of efficiency, rather than having to write stuff down on paper, take it back to the office, mobile devices is really improving technology or improving efficiency in what we do to collect our data.
Yeah, I can speak a little bit about, I would say, two of those uses of technology. So working in the city of Minneapolis, and both in my current role as well as my previous role when I was at the Mississippi Watershed Management Organization, which includes a large portion of the city of Minneapolis, one of our big focuses was in developing very detailed stormwater models of our system. So we've got old, complex stormwater management systems here in the city of Minneapolis with pipes going every different direction and big complicated flow paths, and water moves different directions under different hydraulic conditions. And historically, we didn't really have a good grasp on exactly what was happening within those systems under different rainfall events, et cetera, at least not on a system scale. So over the last 7 years or so, there was a big effort really put into spending a lot of money in developing big, complex models of our systems across the whole city so we could support good decision making in looking across our system to prioritize projects and then see what solutions might actually move us toward our goals. So we put a lot of money into that. Those tools are super useful and have been helpful in, I think, communicating within the technical audience. What we found then at DMWMO, where a big focus of our work was also in outreach and communication with general citizens, is that we found an opportunity to use outputs from those models and develop very simple communication tools that we then put online. And so an example of one of those tools, which I was really excited about, still I'm really excited about, is what we called our travel time tool. And so what we found with our outreach team is that a lot of the citizens that live in the city of Minneapolis didn't really understand that when stormwater runoff came off their front yard, that it went down into a storm drain and went to the Mississippi River. And without that fundamental understanding of where that water went, they couldn't have a good appreciation for how their activities on their landscape actually impacted the quality of the water in the river. So what we were able to do is take outputs from those more engineering tools, simplify them, put them in this online tool where a citizen can now go in online. You know, the interface looks kind of like a Google Maps or something that they're comfortable with, and they can start clicking around on the landscape and see, when a water drop hits my front yard, what's that flow path look like to the river, and how long does it take to get there? Oh, well, what if I'm at the park? Where does that water go? And it just helps them make that connection. And then our outreach team was able to work with them and really build that stewardship in those individuals to say, now let's think about what's happening on those landscapes. If there's fertilizers putting down, if you're putting your grass clippings into the street, what the impact is to that resource. And we found that was really successful, and that was fun to see.
Thank you.
A very general kind of overarching comment about how Internet of Things plays a role in this whole discussion. Marcus did such a terrific job of illustrating how all these emerging tools are just arriving at our doorstep and how it's going to change our world in stormwater, but not just stormwater, but pretty much everywhere. I mean, people tend to refer to IoT as a horizontal rather than a vertical. So that's something that we're following too. So I want to put in a plug for how our state has also got a terrific foundation of Internet of Things companies. We've our agencies just started documenting how much IoT expertise and technology we have here. So grab a copy of this on the way out. My message to you also is if this is an intimidating subject, if you haven't yet jumped on the IoT train, as it were, and you'd like to get connected to some Minnesota experts, that's something that my office would be happy to do. We have a really cool nonprofit here called IoT Fuse that puts on big conferences. They work with companies from every sector. I reached out to them to learn what's happening in stormwater. So you can get that expertise here. You don't have to go too far. If you're asking yourself, well, okay, these tools are cool, I don't have them yet. How can I introduce them into what I do? And then just as one more example, when I reached out even outside Minnesota, I learned about a company that's based in Milwaukee called P4 Infrastructure. They're working with another Milwaukee-based company that does permeable pavers. So they're using IoT and sensors to measure stormwater behavior in settings where these permeable pavers are being used. Well, when they wrote back to say, sure, I'd be happy if you could give this a plug, they said, by the way, there's 4 Minnesota companies that are helping them with their IoT enabling technology. FPI Sensors International in Eagan, Digi of Hopkins, Minnesota, Multitech Systems in Mound View, and the Minneapolis office of SRE. So I thought that was a wonderful sort of testimonial to the fact that that yes, IoT is playing a big role, and it's coming. A lot of it's coming from our state. So thank you for a chance to say that.
Thank you.
Yeah.
I was really impressed with what Stephanie said too about, I mean, I think this is the big challenge, is figuring out how to take information and get meaningful outcomes. I already said that, but this is a great example of what that looks like. But there's a lot of work to do on figuring out how to do that really well. And it's literally about making messages very clear, grounded in strong scientific underpinnings and engineering underpinnings, so that we've got credibility, that we're not in some kind of post-fact world where facts don't matter. They do. It matters where is the model right. That matters to people, and you can prove it to them if you need to. But making it simple enough that we can get real outcomes from it. And it's probably a social science issue and one that is a communications issue, but it is the biggest challenge ahead of us, really.
And I do think, kind of echo what Forrest said too about communications and outreach. I really see technology has changed considerably how we communicate, how we relate to each other, the speed of that, the breadth of that, the scope, global, right? Everything is global these days. So I see some big, interesting changes. But like as Marcus says, we have to be very careful about how we use it for our purposes, right? Not just to use it because it's there, but to get a purpose. So I'm going to open to questions. If we have questions online, if you don't have any posted yet for Marcus or the panelists, please post those. Do we have any other questions from the audience here in the room?
Good morning. Dave Anderson. I hark back to the mid-'60s here. So I've seen a little bit of water in my day.
Is that 1860s or 19? No,
oh, come on.
I played that joke earlier. Right?
Doesn't mean it, and Stephanie, I'd like to follow up a little bit. One of the old adages we had here is, if I can't measure it, I can't fix it. And I'm always a little troubled by, well, the model said. And being on the Citizen Advisory Committee for Rice Creek, I see people that want to give me a 4-digit number for phosphorus, and there's no bloody way that that's real. My question is, how do we assure, maybe for lack of a better word, that our modeling and those kind of techniques are really backed by the kind of information that I think we can now get?
Yeah, absolutely. I think that's a great question and a super important point. I always say we have a tool belt full of tools that we can use to make good decisions and in our engineering world. And modeling is one of them. And then we've got empirical data collection, we've got historical observations, we've got actually talking to the people. Models can't do everything. They make assumptions. They're based off of theoretical data. All models have defaults or things that they're not looking at. And so I think we need to be really careful and honest about the use of them and what they're not properly representing. So for example, a big thing that we run into right now in stormwater models that we've created, they represent our pipe system. They're good at the hydraulics. What happens when we have groundwater issues? We need to be really honest about that application that we've developed is totally ignoring a huge component of the hydrologic cycle. And in certain settings, it would be inappropriate to use the model without additional information to supplement it. So, in areas where we've been doing planning and watershed scale planning that we know that there's a heavy influence from groundwater, taken our models and we've said they're good. And the models that we were creating at the NWMO were calibrated. So we had at least 3 years of monitoring data, flow monitoring data that we were using to create those models. In some cases, we had 8 to 10 years so that we could really look for good storm events and target those storm events that were most realistically representative of what am I looking for the word here? The scenarios and the systems that we were using the models for. So for example, if we're looking at flooding, then we need to find big storm events. So I think the point is that I'm just saying we need to be honest about what these tools are able to do and use all the other tools that we have in our tool belt to monitor data and bring all those pieces together.
You know, one piece that I've found really interesting around establishing trust is being able to show people directly. And the one technology that comes to mind is particularly the ability to use cameras. Like people still largely trust images. Hopefully that'll hold for the near future. I'm not so sure, but it's very easy to show people real things, and we have an opportunity to do that more and more. And like, so what could that look like if we played it out in the, you know, follow your watershed strategy? Is are there ways in the future that we can make that experience even more engaging? You know, is it you know, fly through your watershed down to the river, or something that is actually like marginally entertaining, or you know, that has a way of, you know, drawing people in to engage in the subject matter in ways that are kind of more, I mean, we're very visual people. we people are in general, and showing them instead of kind of telling them, or so they get an intuitive sense of it. It's a lot about, like digital twins is about 3D visualization of these complex environments, and then understanding what the data means in context, so people instantly get it. And in those, you know, the better those graphics are, and the more intuitive they are, the better we'll get response from people.
Yeah,
and they do it because it's fun, right? I mean, too.
And I would say, I think, so there's so much that we can do with technology. So collecting the data, the monitoring networks, developing the models. But then really, I think it's also important, and this is where the historic observation comes in, is to actually go out into the community and say, this is what it's showing us. It says this intersection floods. City engineer who's worked here for 20 years, do you see that intersection flooding or not? And so that's really that ground truthing of observation and history.
That gets back to the human side of things, is that you can do all the modeling and monitoring you want, but until you can verify, you know, maybe you can take a picture, get a drone out there, but, you know, still relying on that human aspect. It's very important.
Well, I mean, perception is reality in a lot of these environments too, and collecting those stories, being able to acknowledge people's perceptions, and, you know, not just dismiss them and say, oh, the model says this, but being able to acknowledge that and include it in the whole story, and is a complicated matter, but one that's important.
Other questions? Remember, if you have questions online, please post them on the Q&A box. Well, I have another question. I kind of want to jump off this concept, talking about modeling, right? Modeling has its place, and data has its place, talking about moving from theory to empirical based. I wonder about the risks, right? There's risks inherent in modeling and making decisions based on that, separating yourself from the data and reality. But I feel like there's got to be risks with basing decisions on data and empirical and the things you're collecting. Beyond accuracy, right, and precision, what other risks could we see when we're trying to do this shift?
I don't mind jumping in. I mean, I think they're significant. You know, for very complex decision-making processes, like transparency and information, like out of context, can be challenging without kind of full understanding of the decision-making process. And, you know, are we going to get to a place where we're able to really convey complex situations really well, quickly enough to catch up with the transparency that's being gleaned? We'll probably get way ahead of ourselves on the availability of information before understanding what it all means. And I think that does have a lot of risk, because, you know, as we see with ubiquitous information being available on the internet about all manner of subjects, like everybody's got an opinion, everybody's got a perspective, and they think they have the expertise to dive in and have a you know, well-formed perspective. That's not always the case. And there are many situations that require, you know, vast experience to kind of even get the context right. So on the one hand, complete information and transparency should like drive things in that direction, but we've seen there are unintended consequences, and I don't think we know what those all are. I'll say on the political side too, one of the biggest worries that politicians have, or really in many leadership positions in any organization, I mean, I could say in an industrial setting, is that transparency looks like risk. And especially where systems are functioning well, introducing kind of new risk that's with uncertain outcomes is a challenge. And so that's one of the biggest institutional kind of pushbacks to deploying hundreds of thousands of sensors to monitor everything, is like, do we want to know what it really says? And do we even have the wherewithal to address the issues that may come up? If that's like a spending issue and a fiscal issue.
I would add that there's, if you're talking about the physical risk of what happens if one of these systems fails, that's what engineers are for, is managing that risk, making sure that there are those fail safes for, if there's a power outage, what does that system revert back to, and protecting, the public safety. So, with our systems that we have put in place that utilize Opti, that talks to the forecast, opens a valve or starts a pump, we do make sure that if those systems were to fail, that either the system will still function to some degree, or that the risk to the public has been minimized or eliminated.
I'll just add too, I mean, there are a lot of these technologies, as we heard with like satellite imagery, they can be used in ways that are not beneficial. Privacy comes to mind around satellite imagery, but around control systems, you can take Internet of Things platforms and you can do things that are really bad ideas from an engineering perspective or from a public health and safety perspective. And I'm glad that civil engineers are the ones that are taking on some of these things in the public space. But there's a lot of innovation and experimentation that's going on that doesn't have those kinds of constraints around it. We see that on the consumer side, that entire companies are running experiments, on us, and maybe not fully anticipating or even considering what all the consequences are. But it will happen in civil systems as well. And I worry about bad design. We don't know what the standard of care is yet. That will play out over the next couple of decades, hopefully in a way that doesn't end up subjecting people to undue risk. But we're going to figure out what all that means. And right now, like as Forrest mentioned, proceed with an abundance of caution, but one that's an enormous responsibility as a civil engineer and a PE, to take that on and say, I'm willing to accept that up front. And that's something that's got to play out, see how it goes.
Other comments on risk?
This is maybe a layperson's comment, but when Marcus said, yes, photography and imagery generally isn't questioned, we've now entered the age of the deep fake, I suppose. Right. And I think even when an image or a picture hasn't been manipulated, there's a growing perception out there that it could be. And I suppose that will be a risk that's with us to a certain extent. Some of it's perception based as opposed to bad actor based, but we still need to be on guard against how people perceive things in this age. Mm-hmm.
So one of the risks, that kind of came to mind for me is, thinking about the data that Marcus showed, that from, the report from 1900, right? Mississippi River data into the 1800s. We have data for long periods of time. We can look at some of those long-term trends, but with some of the new sensor technology and data storage and collection rates, we're having this whole new age of big data, right? So how do we manage short-term observations, high data with long-term trends? Where do we have to be careful about making decisions on this relatively short, big data collection? Is that really real? Is that long-term? Is it short-term? Do we make decisions on that? How do we manage that system? If you have comments on that.
Long-term adaptive management, I think, is one of the terms that Marcus used. Knowing that if you're making a decision based on that short time period of data, that you have the ability to go back look at what happened after you made that decision and change if necessary. And I think that's a management style and a decision-making style that Capital Region is very cognizant of. And these tools, this data collection, these sensors are there so that we can more quickly look at that data, see what's happening, and then make different decisions, or say, don't change anything, it's still working.
One of the dangers of living in a time when we are, even you look at this stationarity of rainfall data. Does the past actually tell us what we should be designing for or not? And then it's very comfortable to rely on hard data for understanding probabilities. This is what civil engineers do. But we are kind of around all the edges in all parts of what we do, questioning whether that stuff is right, whether it represents the current conditions, whether it represents future conditions. And it's hard enough to convey, particularly to the public, the fundamental principles in historical risk, like what is a 100-year flood, but then to introduce and say, well, we might not even be right about that. And then what are we sure of? And I think it's a challenging time in that regard. I think the adaptive management strategy, can we think differently about design? If we may need to just step back and say, we don't know what the actual design value is, but we want to build the system so it can be flexible and take into account, I'm designing for the 100-year storm, and here's a passive system, and if I'm wrong, I'm gonna have to rebuild it, which is like our historical way of doing things. You may go into the design problem saying, this is the best information we have. There's a pretty good probability we're wrong, and how do I design for that condition? That's something that's just not taught. It's not how we've been established our regulations or design standards. It's not simple, but I think we really ultimately have to figure out how to do that, to design robustly with uncertain inputs. Not easy. It's easy for me to say, but it's not easy to do. Yeah.
So maybe I'm going to shift gears just a little bit. We've kind of talked about some of the risk and challenges and things we need to be wary of and cautious of. But I also want to highlight a lot of the benefits and things that we've seen in terms of technology. So maybe specifically, where have you seen technology working really well, whether that's in communications with certain groups or certain peoples, or getting out certain messages, right, specifically? Or where is it more easy to kind of get that message and get engagement and get people involved in technology? We've heard at least one example already, or two or three. So are there others? What are ways that we can really make good use right now with what we have in technology in advancing this message of protecting water resources?
I'd say, in my experience, technology has been really well received by some of the more urban audiences that I've worked with. And maybe it's just because they're more used to using it in their day-to-day, or maybe it's just the era and kind of what I was doing for my career at that time and where we are as a society. So it's a little hard to know exactly what that is. But in addition to the example that I shared about the communications tool, more recently, we were putting together just some images that were conveying some of the data that we were collecting in our monitoring system about, say, the performance of best management practices, and putting together some simple infographics and making those active and using them with high school students or general community members to say, we've captured this much water, we've used this much rainfall to irrigate this field and save this much potable water. And those were really fun and rewarding tools to pull together, and I think received really well by the community, again, toward this education effort. And I think, those targeted at the youth and, just their comfort level. I think the other places that I've seen that being successful, again, more toward the education side, is when those tools are then coupled with an educator or somebody who's physically present and helping audiences to engage with and interpret what they're seeing on the technology.
a technology that is doing well elsewhere and is just being introduced here. So I hope that we'll soon have some news here. Is a Dutch company that is quite new. They're called LG Sonic, and I was reminded of them when Marcus was showing images of how nasty these algae blooms are. Have you heard of LG Sonic?
I know
Marcus?
them, yeah.
Okay, so for those of you who haven't, this Dutch company's figured out a way to treat algae with sound waves. That they've got a proprietary signal that disrupts the biology of the algae and causes it to sink. It's an interesting new way to actually deal with an algae bloom rather than throwing chemicals in the water or other methods. They've done well. It's a Dutch company that's introduced this technology in a couple of places around the US. I heard now in Minneapolis for the first time. So somebody's at least trying it out here. So I hope that we'll have more news about that one in the future.
Other places I've seen technology be really useful is in, integrated water resource management. And I think when you've got a group of stakeholders who are engaged and really want to come forward and look at a water management issue, and the use of modeling tools to help bridge some of those gaps and pull together the pieces of information from each of the interested stakeholders and put them into one common platform that you can then use to simulate the system and make kind of group decisions around that. I've seen that, time and time again become a really useful tool for those types of situations.
I know with one of our capital improvement projects, we're seeing, or we saw during the design phase, an actual cost savings for a landlocked system where we were experiencing flooding, and we tied a surface basin to an underground infiltration basin, and by adaptively managing the water level, drawing it down in advance of a storm, we increased our total storage, our flood storage, by about 58%, something like the equivalent of 290 linear feet of 10-foot pipe, where we didn't physically have the space to put that. Confined to a very small park. This is our Curtis Field project in Falcon Heights. And that 58% increase in volume was only a 14% increase in cost. So rather than, even if we had the physical space, we would have to purchase that pipe, install that pipe. But instead, we focused our investment in actuated valves and sensors. So, as a public agency who is using public funds to protect water, protect our water resources, we are responsible for providing systems that work, but are also, cost effective. So another in our monitoring field, our monitoring division, they have taken some technologies such as remote data access to our stormwater sites, where we're physically taking samples from storm sewer systems. And we now, before we had remote access, staff would have to physically go out, look at the ISCO sampler, did it trigger, are the triggers set correctly? But now through solar panels and cellular connections, we can, our monitoring staff can see if something is functioning, if it triggered. So now it triggered, so now go physically get those samples. So they have been able to greatly reduce the amount of time spent traveling to sites. And then that opens up time to actually analyze all the data that we're collecting. So
I do think Forrest's example is quite good around detailed technology applied on a specific project. I think stories are really important, and particularly for the public, just focusing on the outcomes. I mean, they are very interested, and I'm an engineer, so like I'm so excited about telling them about all the details of the technology, but I've had to take a big step back from that and say, like, people want to hear what the result is. We saved this much money, we prevented flooding. And by the way, how we did it is really interesting if you want to know or hear about it. But telling that story, particularly like at a watershed scale, it's really easy to come up with these big metrics, and nobody knows what they mean. I said 1 billion gallons prevented. I mean, nobody here knows what 1 billion gallons even looks like, right? It's a big number. Marcus said a big number, but it's probably not the best message, which is probably Forrest's, where he says, here's a neighborhood and they had a problem and the field flooded and we saved this much money and the field doesn't flood. Like, that's a more compelling thing to tell people. And by the way, we're going to do this 100 more places, right? That's a more interesting story than some big metrics. And data has the propensity to get us to focus too much on the details and not tell stories as well. So I don't know. That's more about the messaging and how do you do that. But that's the example for Ormond Beach. It's one of the most interesting things to tell about Opti, because people can say, oh, that neighborhood flooded and then it didn't flood. And like, I don't have to explain 2 hours of like how it connects to the internet and how the cloud infrastructure works and the security protocols and what the sensors are and the size of the pumps. And like, yeah, an engineer would love to hear all that, but they just want to see what I showed. 2009, it flooded. Hurricane came, it would have flooded, it didn't. and then talk about the outcome. So, I think it gets back to that standing around a monitor or a dashboard and somehow having an insight about how the world's better. What people want is they want to live in a city that works. That's literally all they want. They want to come out their front door in the morning, go to their car, and drive to the store or go to work, and not be restricted by localized flooding, or they just don't want their basement to flood. They actually don't even want to know anything about it. They just want their city to function. And if we can get there and tell simple stories, even if the stories like at a detailed level are incredibly complex, they want to know it's there, but they don't necessarily want to know like how the sausage is made. So,
and I think that's I just want to echo. I think that's one of the advantages or maybe advances in the digital age now, is stories and communication and entertainment age. Right, we're in the entertainment age. Dazzle me with this stuff. Those are some of the things that we could take advantage of. Focus less on the details, unless the audience is for the details.
You have to have them there if they want to dive in. Yeah.
Correct. You have to have the details. You have to have support for what you're making your decisions on. But when you're talking to a broader audience, convey that message appropriately, right? And we can do that. Did you want to add something on that?
Very quickly, and one more technology story, and just the way Marcus couched it in terms of, well, people care about the results, and how it happens sometimes is less important. So I'll start with the result, and they'll tell you how they did it. There's a local company called Summit Enviro Solutions that helped the city of Edina save about $60,000 a year in energy costs on a single pump. So that's kind of the punchline. How they did it was through exceptionally talented 3D modeling of their aquifers, so they could tell them when to turn the pumps on and off. So when you see the images of how they do that, that gets into the weeds that some customers won't care about nearly as much. But when they hear you save $60,000, well, that's a nice ending to that story.
Yeah.
So that's a local company, and I've got some info on them if that interests you more.
Well, and even that is an example of could be a 20-minute presentation, right? On exactly that project.
Yes. Yeah.
And you just shared it in 30 seconds?
Yes, you're
and
right.
got the message
Good
across.
Stories do count.
Right.
Exactly. I want to hear more. That sounds great. I mean,
Exactly.
that's really a neat one. Yeah.
That's really what we need to do, is pique the interest, right? It looks like we might have a question from the online audience.
Okay, the question is, with all of the disruptive technologies that have emerged in the last couple of years and decades, and many more to come, how can some of the regulatory agencies be convinced to incorporate these advancements in science rather than degrade to the lowest common denominator? An example being EPA industrial stormwater compliance still only requires grab samples.
It's a super difficult challenge. Across the board, I mean, it's not just an environmental regulation, but regulation in general. Technology is moving way faster than our political system can keep up, or even understand what's happening. Even to get anybody to get their heads around what's really happening kind of across the board on the technology side is really difficult. I don't have a great answer, I think, about how to fix that, other than, it's going to happen. Ultimately, many of these things will probably be settled outside of traditional regulations. This has been true for a long time in water quality and relative to Clean Water Act is the Clean Water Act has some very broad goals. That doesn't mean that the regulations developed to achieve those goals are even legal. And at times, lawsuits are the primary thing that drives actual action. I would suspect that lawsuits, unfortunately, will probably be the way that this proceeds going forward. You know, if you've got ample data to demonstrate significant environmental damage, the underlying law is there to be able to act on that, regardless of the regulations. And I would see that continuing to play out maybe in a much more difficult way. I mean, it's basically regulation by a consent decree and lawsuit going forward. So, I mean, unfortunately, that's how we've made the most progress, frankly, under the Clean Water Act, is this cycle of regulations and lawsuits and that delicate balance.
Go ahead.
I don't have a great answer. I don't know. Ask me in 3 years, I guess. I guess in my experience at the MWMO, we were non-regulatory, and the whole mission of the organization is innovation. So it was pretty easy for us we wrote standards and we had goals for our projects, but then again, we created those to be flexible and to allow some level of interpretation. And then our staff would work with kind of the technical staff, the engineers, to look at what those solutions looked like. And we were intrigued and always encouraging, kind of pushing the envelope and bringing in more innovation and technology. So I think that's the way they were doing it. But again, they're not a regulatory agency. So I think that allowed them a lot more flexibility to do something like that versus being at a city. So I don't know if you have, so Cap Region is regulatory, if you guys have examples of how you've done that.
Well, I think one way we try to push the limits and get things maybe not directly into regulation, but showing, just like Mississippi WMO, be a leader, be innovative, try these projects, try these products out, show what does work and be honest about what doesn't, and be on the cutting edge and see. You have to show people this works. Here's how we can save you money. Here's how it's going to be better. So on my non-regulatory hat, there's the work the district does on our own projects where we're really trying to show the water resources world that there's a different way to do things. And if it doesn't work, I think it's important to tell that story. On the regulatory side, the regulations have to be based on science, and you have to listen to your regulated community. We have a technical advisory committee that convenes regularly to listen to those that are being regulated. And as going back to the post-regulatory world, it's going to have to go back to telling those stories, and the community has to support the work that you do. And that's the only way. We're very fortunate within Minnesota to have watershed districts that have rules to require developments to incorporate stormwater management practices. So, we have a little different perspective than just the federal level, but I think Marcus's point of the post-regulatory world and the human interaction, telling the stories to get the support, because watershed districts maybe someday could go away if there's enough pushback from the community to say, we don't see the benefit in this. We don't think that it's a smart investment.
Yeah, I will say, I mean, you can look at I hate to keep going like these history stories, but anyway, I mean, you can look at like why does the Clean Water Act exist? And you can go back to the Water Pollution Control Act of 1948. The basic underpinnings are interstate commerce. So you've got like individual states, in the absence of a federal regulation, you've got individual states that had their own rules, and yet they all impact each other. Like, in the Mississippi, we're all in it together. And if you don't have good regulations in place, what you end up with is legal anarchy to some degree. And so you need some, you need coordination at scales that make sense. And, watershed management districts are a nice structure at an appropriate local level to bring that kind of combined interest around a resource together. And I would say, to what Forrest was indicating as well, in the absence of, the federal government or states acting, it is really the local entities that are driving things forward and getting action. And it's much more responsive to what people want. The challenge is we can't take on Gulf hypoxia by, at the watershed district level. You have to do big things. You can try, but you've got to get a whole bunch of neighbors involved and downstream folks. But, so I think they're at the local level, you can be very responsive and do really interesting things and on the regulatory side. But it's kind of the fundamental role of regulations to step in to avoid using the courts as the only way to reconcile conflict. And that's basically why we have larger scale, state or federal regulations in the first place. So I'm always convinced people talk about some of these things getting weakened, and the reality is the outcomes will be the same. They're just way less efficient at achieving those types of end goals. And it's anarchy. It's legal anarchy from that perspective.
So we'll take another question from the audience here.
I have a comment or two or three, if you don't mind.
Excellent.
I was very impressed by certain things in your talk, particularly how technology of a simple kind can be used very efficiently to solve big problems, such as using temperature sensors for 5 cents a piece. Actually, I need that address. However, and there are other applications to it. You have gazillions of data from satellites. Even surface water quality on lakes can be identified very well. And I'm referring to a guy who worked here at this laboratory who did that 40 years ago for the US Department of Agriculture, and did some very interesting work on that. I also was very impressed by your visuals that showed the high resolution effect that you can harvest when you have huge quantities of data, such as the maps of the US, where certain problems exist or certain quality parameters are not met or exceeded, etc. Maybe we can also do that in terms of enforcement of water pollution. If we had more detailed measurements and more frequent measurements, we might be able to do a much better job to prevent the bad discharges that we care about. On the other hand, as Stephanie pointed out very strongly, in the modeling field, the validation of the models also would benefit from more data, but I think there are some very serious limitations in that field. And the problem being that modeling has a huge shortcoming in the assumptions that have to be made to describe whatever processes you want to study.
Right.
If you are fortunate enough and you're a chemist and they come to you and they say they want a substance with these and these qualities, the guys up on campus who figure out what molecular structure you need to get those quantities. That's not bad. But if you're modeling water quality and the physics and the chemistry and the biology all come together, I think we'll be at work for a very long time trying to have water quality models that can do all these things, even if we keep on measuring water quality in every square inch on the globe, because we cannot describe the processes at a fine enough scale and the wizards of the past have told us everything is connected to everything else. Well, you show me which model catches that description. And we have to make assumptions. We have to need both assumptions. And what do the models do? Well, after they find the shortcomings, they look for correlations and start putting those in. Well, already that's a giveaway that things are not as well known as they should be for the modeling purpose if you have to put in correlations, because the chemists, they work at the molecular scale and they are much more successful doing it. I think I'm very intrigued by the technology and all the fantastic possibilities. And I wish I could come back in 200 years to see what has been done. But there are limitations. No matter, even if we drown in data, there are certain things that I think we will not be able to do with as much resolution as we would like to do. And I think the hurricane models that they show us are a good example of that. There have been a lot of people, very smart people that worked for a long time. And what do they present us?
A cone.
A cone and 20 different lines for the potential passage. Yeah. So these are my comments and my thoughts.
Yeah, I would. I mean, a couple of interesting things there. Well, I don't know how I feel yet around, more black box models like machine learning approaches. I think we'll see a lot of evolution in the ability to predict results, but we are at the same time losing our ability to understand why. And we are getting ahead of ourselves on being able to forecast without understanding how to do that. So there is a big push toward these highly empirically driven machine learning and deep learning approaches to get around some of the limitations of the parametric models. And like I said, I'm not, for me, the verdict is still out about whether this is even a good idea when we can't explain why. We know something that we know, but we can explain how well we, probabilistically understand it. The interesting thing about like the hurricane models is they're probabilistic models. Those cones are accurate. They're just not deterministic. They're statistical, and that's really uncomfortable. So things like machine learning strategies are also statistical in the end. They say, here's the outcome, and I know with 99% certainty that, this is a cat or something. But it doesn't say it is a cat. It says, this is what I've learned from the empirical data. And I suspect we're headed like increasingly into a world like that where we can predict things, but we can't explain to people as well. And I think for civil engineers, at least for me, that's somewhat troubling. I guess it's always been true with statistics in general. They're really hard to explain. Like, I'll just pick something easy. The mean, okay? You can take 100,000 data points, and I can tell you what or some really large number, what's the mean income of people in the United States, okay? We can say what the mean is. And it embodies all of that information. It's a single number. It rolls it up nicely, simple, understand metric. And yet, like, I can't easily explain to you with just that number without digging into, some more detailed tools. And here's a histogram. And by the way, here's all the raw data, like what's really going on. But it's useful in certain contexts to understand, what's going on with incomes in the United States, right? I think we end up with similar results in some of these modeling contexts. The other thing that I find really interesting with increased data collection is we have these massively over-parameterized models that we think are incredibly accurate, right? I mean, the Chesapeake Bay model is one. We've got very few actual measurements of water quality, but then we have land use data, literally millions and millions and millions of pixels, where we went from, single-digit watersheds down to like literally microscopic entities as part of the model. And those things are incredibly over-parameterized. You can calibrate to any result you want, and you don't know why. And you could turn all the knobs a different way, and you'll get the same, you get the same result for the calibration data set, and you have no idea if it's predictive. I think we're headed more and more into problems like that where we have more data, like in some areas, and not the ability to validate, as you said, or to calibrate the models well enough. And what that looks like is that we appear to be more certain about our results than we really are. And that's not great, especially from a public perspective. So maybe I shouldn't keep talking, but one really cool example that hits your point home that came to me at a modeling conference in Boulder a few years back was there was a paper on the age of water in streams in, I think it was in British Columbia, and comparing the actual age, and they were using isotopes of oxygen to be able to determine how long it's been since the raindrop fell, right? You can do this, which is incredible. I'd learned at this conference you can do this. And it turns out, you know, all the mechanistic parts of our model to determine the hydrology in the stream are just wrong. There's all these interflow components on the groundwater side that are fundamental to the process that aren't included in the model at all, but the model predicts incredibly accurately what the hydrograph's going to look like. It's just not the same water. And so you put like on top of what we think is a really well understood hydrologic model, water quality or something, and you just get it completely wrong, which is the age of the water is not the age of the water. Or relative to green infrastructure, how would that play out? Is we say, oh, look, we put a bunch of bioretention cells in and the hydrology is the same. Isn't that wonderful? And the question is, well, does that mimic the actual processes that are happening in a natural system or not? And the answer is like, we don't really know. We would have to study it in a lot more detail. So I think you're right. I mean, that's just a good example of a bunch of assumptions that fit the data perfectly and predict the outcomes incredibly accurately, but they're wrong. So I think we need to think about that really closely, as you indicated. I don't have the answers. That's the other part of my answer. So,
any other comments to that? Well, I think to close then, what I'd like to do is give each of our panelists a chance to respond to this. Think in near future, right? 2 to 5 years. Where do you see the biggest opportunity to advance stormwater, water management, water resources, water quality using technology? Maybe we'll start with Forrest on that end and finish on this side.
Sure. I'm not going to pretend to be on the forefront of this technology side. I think I'm very fortunate, like I've said before, that we're skimming the surface right now. A lot of the stuff that Marcus is talking about is just mind-boggling. And you know, I don't know where the biggest opportunity is, you know, whether it's increased accuracy or in our models or just, you know, improved efficiency. But I just want to say that I'm really excited about the potential for improving what we're doing and you know, realistically and conservatively incorporating technology wherever it makes sense.
Yeah, so I'll answer from my viewpoint at the city, which I'm so 3 weeks into it, right? And I'm learning about all the technology tools that we have at our fingertips as a division to manage the resources that we're in charge of and our infrastructure. So everything from creating repair tickets and sending iPads out with staff in the field to actually do that work that was historically more paper-based, and how that can, if the systems are set up and functioning correctly, reduce workload and be really efficient, similar to what Forrest was sharing with what they've been able to do with their monitoring team, but how you have to be mindful about that and use it in the right way. I think what I see, and just to kind of step off of this example I was giving about these resources that we've now developed with our stormwater models, and what I'm excited about is to actually see our city move forward and use them, and to do this system scale planning when we're looking at capital projects to try to manage our infrastructure better. And so recently what we've been doing as a city is looking into some optimizing software to go in and look at different scenarios of, you know, across these 2,000 acre pipe sheds, maybe there's, you know, hundreds, thousands of pipe segments and lots of different scenarios of where you could look at implementing different best management practices, green infrastructure, whatnot, and drawing out scenarios and feeding them into these optimizing software that helps very quickly run through different scenarios, which, you know, historically when I was in the consulting world and doing this 10, 15 years ago, what I was doing is putting physically each different one into the model and hitting go and then sitting back and waiting for it to run for 4 hours. And then, you know, I'd get an answer and I'd pull it into a spreadsheet and try to look at the answers. And that's, you know, so it's more time efficient. I think what the jury's out on a little bit for us is, are we getting better answers out of it? And so that's exciting to me. And I think that's our next 2 to 5 years worth of work in our team.
Just a very simple observation about our IoT revolution and the fact that it's in its infancy. Big data is great too, but one comment I hear from people in this field a lot is that our capacity to interpret isn't really keeping up. And I hope that we make some progress in that department. We just heard some examples about how the models are lacking. That's maybe connected to the problem, but also it's not good enough to just install 1 trillion sensors into everything and then not be able to interpret it at the same time. And then also in closing, if you like this topic, I hope you'll also consider coming to the Gray to Green conference, also hosted on the University of Minnesota's campus. It'll cover this subject and a whole lot more in the world of green infrastructure. Pick up a flyer on your way out, please. Thank you again, Andy.
Yeah, and I've said a lot, so I would reemphasize making you know, around technology choices that result in real outcomes. You know, so really, I think we can do that pretty easily. We've got a lot of things we can do, and picking the things that are the most valuable to focus on, and really, you know, digging in on those and advancing those technologies where they result in real change in relatively short time frames. The optimization side is a huge opportunity. And again, I mean, I think the stuff Stephanie said is right on, which is like, it's totally approachable now. We can incrementally use the kind of horsepower we have around computing to consider a much wider range of options. That's pretty easy for us to do. I think that's probably the near-term, you know, benefit of these technologies is you know, optimizing existing systems we already have instead of disrupting or kind of reinventing everything. So.
Well, great. Thank you so much, panelists. I want to thank the audience, both online and in person. This will conclude our seminar for today. Please help me thanking our panelists.